Okay, welcome. So this is the system responses class on the digital signal processing problem solving. And today we are actually talking about what kind of output any system may have for certain input. And let me open the today's show. Wait a minute. There, full screen. Okay, so we talk about system responses. Most important response for a digital system is an impulse response. The impulse response basically defines the whole system, what it is all about. It's basically quite close to that. On analog systems, you would do some system analysis using the step response because the impulse is quite hard to make in real life, but in digital world, this piece of cake. Basically, then you can test any system by feeding an impulse in and getting the output. So that's basically what a system impulse response, how it's defined. Impulse in, here is a system, whatever the system is, linear, non-linear, causal, non-causal, the stable, unstable, whatever it is, the impulse response is defined like that. So for example, for 4-point running average filter, where the difference equation is something like this, then the impulse response is simply you replace X with delta and it looks like that. So that's what comes out from 4-point running average filter. Okay, in natural world, we have only infinite impulse response systems, unless you are dealing with some quantum mechanical phenomenon. So all natural systems are the infinite impulse response systems, meaning that the impulse response never ends. It's just when you get an impulse comes in, then the this system usually on the amplitude decays and then there's some oscillation there. That's atypical behavior of, say, second or higher order system. Or if it's a first order system, then it's just the signal decays. So practically, for example, let me turn on my camera. I have now a new setup. Not that setup. Where's the where do I have my camera? Camera. How can I change my camera? No. What? Oh, it may help if I plug in my camera. Sorry about that. So now I should actually have the settings also for, maybe I just need to restart this one. Much better. Okay, so I have my new drawing board. Okay, so high tech, very high tech. So for example, if we have a digital system which resembles a, let's see, low pass filter. or RC low pass filter. If you get impulse in, you basically get, no, sorry, high pass filter. You get the envelope, exponential envelope, and the impulse response would look like that. It would have the exponential decay there for RC low pass filter. And this is infinite impulse response system. So IIR systems, they are more or less looking like this, or say it might have actually these negative values, and so there could be some damping oscillation there for stable systems. Unstable systems, this would go haywire. For FIR systems, we have a, okay, well, it could be something, oops, something like this. And then zeros, meaning that the after some point the signal goes to zero, not near to zero, but exactly zero. Okay, there's a very simple way of actually testing or how many samples you need to get, but I think it's later on. So finite impulse response system that basically has a the finite h of n, but infinite impulse response system, they have the infinite series of values coming on. Okay, which means that practically when you're calculating a filter, you have a difference equation. If it's a FIR system, then you can calculate it directly from impulse response. So the same way as 4-point running average filter. This is finite impulse response system, and actually this h of n is simply looking like this. Can be directly calculated from the difference equation, but on the other hand, if you have infinite impulse response system, then this does not work anymore. You cannot take just this h of n and use these calculations. But what you need to do basically is to have some feedback on the system in order to calculate it. But that comes actually from last week's systems. We had these the systems with feedback. Okay. Okay, then transfer function and impulse response. So transfer function is simply the Z transform of impulse response. The same way as in analog domain, the step, you calculate the step function, and then you can actually calculate the step response using the Laplace transform of the step response and Laplace transform of the input, or Laplace transform the step, and Laplace transform of the system transfer function. Then you can calculate what is the Laplace transform of output, which is then a little bit tricky to get back to the back to the signal. But anyways, in digital domain, it's a little bit easier since we are dealing with the impulses instead of steps, and system output for unit step input. Take the Z transform, then basically, and what is Z transform? Maybe your mathematics teacher has already told you about it. It's one of the discrete the mathematics tools, close to Laplace transform, very close. Instead of integral, it's a sum. So practically, for example, on the 4-point running average filter, if you want to calculate the transfer function, you take the Z transform of the impulse response, which just happens to be something like this. An example. There are more into it, but anyways, I have skipped some of the theory of the properties of Laplace transform. Oh, we had it already last week. Yeah, I think we had it already last week. So now only new thing is here that it's a special case of this system transfer function versus difference equation. So now we have a special case of that one, meaning the impulse response versus transfer function. Okay, zeros and poles. Those are pretty straightforward case. Actually, finite impulse response have all poles at origin or cancelled by a co-locating zeros. So this is the 4-point running average, both of them. This is the straightforward case of feed forward only, where you have more calculations. Then we have the zeros on unit circle. And then we have triple pole at origin, so it's a finite impulse response system, as we could actually show it already here. The impulse response stops at fourth term. It goes to zero and stays on zero. Okay, actually that's also the trick where you start looking at the if the system is finite impulse or infinite impulse response system. You basically have to look only these values after the highest order delay. So here we have the highest order delay is 3, right here. And after that, actually already the fourth term and terms after that are all 0. So that's the brute force test for this one would be to just check the if there are any non-zero components after the third delay. Okay. But anyways, so this is also the same finite impulse response system with the zeros, where there are zeros and poles like the previous, but there's also that funny zero pole at point 1, which basically cancels out. So the poles is cancelled by a 0. And that actually is the same as multiplying the transfer function with 1 minus z divided by 1 minus z. So we multiplied it with 1. And it actually on the feedback the form of the zero pole plot of running average, it looks like that. So there's a cancelled pole. And system is FIR. Okay. If system is infinite impulse response system, a linear time invariant system is IIR, then it must have at least one pole somewhere else than origo and without any canceling zeros. So even one pole somewhere in between 0 and the unit circle would make this system a IIR, or actually if it's outside of the unit circle, then it would be also unstable, but still IIR. Okay, step response has, say, a little bit less use in digital systems than the impulse response, but it has some applications. Which I will talk one special application next week, and it relates to the system characterization. So we have the step response, which is simply the function. Okay, we have the any system, we have the step input, and we have step response output. That's the definition, basically. Then it means that on 4-point running average filter, we have this kind of, so we have the, well, no magic here. And what it looks like this. So the unit step response of a running average filter looks like that. Okay, not a biggie. Anyways, then you can already start looking at what is the rise time of the system and that kind of things. If you think it a low pass filter, it's a low pass filter, then you can, okay, you can already define the rise time and such kind of things if you want to. Just a brief note on stuff I will be explaining more next week. Oh, I need thicker paper maybe, or a real whiteboard here. But anyway, so think of any analog system which is defined by h of s, and you have a function generator and you run basically a step, meaning square wave input. That's the thing that you probably have done on your electronics lab. And what comes out is roughly the step response, which would be S of t. So if this is x of t or u of t, but anyway, you can then sample this with the digital sampling oscilloscope. So if you have DSO here, and you get this, for example, something like this as an output. So this is actually a S of n. Okay. Think of the one of the previous stuff. So delta n is actually mu of n minus mu of n minus 1, which actually means that 8 for linear LTI systems, if this was a linear system, this would actually mean h of n is s of n minus s of n minus 1. So practically, you just take the first order difference, or this is also derivative in one sense, and you have the impulse response measured from a real system. And this impulse response can be then used for characterization of the system. Okay. One way of digitizing a system. Okay, and then let's see, arbitrary signal response, the same as last time, I think. So if you have any signal f x of n, then you can calculate the output as using the difference equation. But okay, just a reminder, when you're dealing with the embedded systems with limited limited calculation capabilities, limited performance, then it really matters how you reorganize these calculations to make as little as possible calculations. Memory is cheap to save these values, but calculation is expensive. Usually the multiplication is slower operation than addition operation, so you try to have as little as possible multiplications, but also the number of the operations is the key point here. Number of multiply accumulate operations, which is one measure of digital signal processing performance. How many max a system can do in a second. Okay, so but optimizing a filter, it's a state of art, and on the other hand, you can go really far with only using a plain engineering logic like this one. Okay, so those were the time-based responses. So we have impulse response, which defines the system. It defines the transfer function. Then there's the step response, what you can use to recognize of a real-life system, for example. And then we have the arbitrary signal response. Those three responses in time space. Okay, then we have this ugly formula. I really want to find you a better formula. Do I find it? Maybe I should draw it. So your system transfer function evaluated on the unit circle is the frequency response. So on the unit circle means that Z equals to e to j omega. Okay. Maybe I'll, so, okay, it actually states there, but this is still ugly. It's still ugly. Ugly formulas. I hate ugly formulas. But anyways, when you have the e to j omega on that form, that the transfer function is the sum of bk times z to minus k and divided by sum of ak z to minus k. Then you have that first part here, that kind of frequency response, the formula, or then you have also the other formula, which is the which actually ties it into zero pole plane. Same thing. It's just the this product formula. Okay, and if you have a complex calculator, just like MATLAB, this is a piece of cake of calculating these. Okay, and it gives you complex numbers. Complex numbers, and the same way as in analog world, the absolute value of that frequency response is magnitude or amplitude response, h of ej omega, and then there's the phase, which phase angle of that that the frequency response is the phase response. Same thing as in analog systems. On the graphics formula, actually, on the z-plane, you have this complex unit circle, and the e to j omega is a point on the unit circle. And it actually makes some sense when you think of this product form, where you have the zeros and poles of the system. Then you basically have this point minus zk. Let's make a very small system here. Okay, that we have the zk, for example, here and there. And then we have the poles, for example, just simple double pole at origo. Okay, and then we have e to j omega. Let's see. Let's pick up some color here. So that's the point e to j omega on the unit circle. So with that product form is simply the difference vector of that point to 0 locations, and you multiply those, and then in this case you would have the denominator as something like 1, I think, since you have the pole locations both are at 0, so at least the distance is 1. The angle is angle is something. Okay, can't think of it right now. Oh, it's just e to j omega. Okay, so it has a graphical the representation also, this frequency response. Okay, and it looks like that. This is actually the 4-point running average filter. Magnitude response and phase response on normalized frequency axis, meaning that this is the 0 frequency and this 1 is the same as the phase angle is pi, and phase angle is pi. What next? Yeah, meaning the sample rate over 2. Yeah, so 4-point running average. So e to j omega is actually cosine omega minus I sine omega. So it's, well, there is a, oh no, sorry. The frequency response is that one, and taking it into account of that formula, you can actually have a closed form formula for frequency response. On the other hand, it doesn't much makes sense. We are in digital domains. Usually it's faster to calculate things than than to start using those symbolic functions. Okay, there we have the normalized frequency. So normalized frequency is frequency equivalent to cycles per sample, and for known sampling rate, that omega normalized frequency is 2 pi f divided by fs, meaning that at omega angle pi, you are at sampling rate over 2. At 0, you are at DC, or if the omega goes to 2 pi, then you are at the sampling rate again. and actually 4 pi would be at the same point, and so on. So it's a repeating spectrum. So 4-point running average filter frequency response at sampling rate of 44.1 kilohertz. It would look like that. So you get some physical meaning for the horizontal axis. Okay, amplitude response and zero pole plot. Back to the business. We have the zero pole plot. For example, here we have the 3-point running average filter zero pole plot. We have the angle omega and the point EJ omega here. Sorry about these lines, they go haywire. So practically, maybe I should actually draw it by hand. There we go. So we have this amplitude response. Oh, the formula is also going a bit funny. Okay, it must be something to do with aspect ratio of this screen. So, but anyways, we have the transfer function. It's and evaluate it at unit circle. Calculate the norm, which is the amplitude response. We have the absolute value of C on the beginning, and then we have a product. I will open it up, the product, the absolute value of those. So basically we have absolute values of each of these individual differences. So we have e to j omega minus z01 times e to j omega minus 0.2 times e to j omega minus 0.3. This, and then on denominator we have the same thing but for poles like that. And we have the zero pole plot, third order, and then we have the zeros here, imaginary axis and real axis, and we have the e to j omega point here. Okay. This, if this one was the 0.1 here, that part is the distance of e to j omega minus z1. So the next one, for example, here, this would be that distance. And then if you have that distance. So graphically speaking, the amplitude response on zero pole plot, you can start measuring the distances from that specific point at that angle, meaning at the physical frequency F, and you can calculate these distances to each zero and each pole easily. Okay. So that's why what I had here. But these colors and those don't quite match. And let's see. Let's take a quick look on one animation here. Animated GIF. Come on. Okay. So that's a 3-point running average filter on a linear magnitude scale. The amplitude response on linear amplitude scale. On digital systems, usually you show this frequency scale on non-natural linear scale, but usually the magnitude is shown in decibels. But anyway, so that's what happens when you calculate the transfer function, those distances to each point separately. And okay, let's see what happens. Good. So couple of points there. So if we have any zero pole plot, let me open up a new page on my drawing board. Amplitude response has local minimas on the angles of zeros. Adding 0 at the unit circle results in attenuation signals. And amplitude response has local maximas on the angles of poles. Adding pole near unit circle results in gain of signals. Okay, so before going to those animations, I'll show you just what it in principle looks like. So if we have any system, and you want the amplitude response to go 0, for example, at high frequencies. So this would be sampling rate over 2 here, sampling rate over 4. So on omega, this is pi. This is pi over 2. So you want to deep the frequency response to go 0 at those angles. You put zeros at those angles. You have a local minima there. Then you want to have some basically local maximas so that you can adjust the gain. So practically local maximas at those angles. You would add these poles. So maxima to adjust this as the that will be a unity or a flat passband response. Okay, and then couple of poles on those angles, and okay, that is somewhere in here. So you just translate those angles to here. And that's a low pass filter design. We could actually test it just for fun if it works on the with MATLAB. But anyways, so that's a one way of say eyeballing system zeros and poles to make a nice working filter. Absolutely not optimized filter, but it can be done also like that. Anyways, two more animations. Since I made them, I make you to watch them. Okay. So moving just zeros on the unit circle. You have the local minimum moving. Now I'm moving the pole. So that's actually double pole closer to the unit circle here. And the closer it gets, more gain you have. And then if you split that to 2 poles, then you can actually start moving the pole around wherever you want. And then it goes over again. Then there's how to make the flat response. Okay. Come on. Maybe you have better. Of course, it opens up immediately when I close it. I have a slow the DSL, not DSL, but the 4G line. Okay, so flat response. Okay, so I have 3 poles located at those angles, and actually, this is a one of the filters you would have really bad trouble in analog domain to do this. You can do a flat response for analog filter for passband using the Butterworth approximation, but then you would have some trouble of having those zeros on the S-plane, the imaginary axis, which means that you would have an RL the path there without any resistance. Okay, so let's go forward. So that was the frequency response absolute value, which is the magnitude or amplitude response. Then about the phase response. There are 3 different phase responses depending on how the system actually changes the phase of the signal. One which is 0 phase response, meaning no delay on of the signal. It can be done on digital domain for if you do post-processing of signals. Okay, so analog world, you cannot do a 0 phase response system. Well, actually you can. It has only resistors. Not really interesting systems at all. If you add there any inductors or capacitors, it immediately means that you would have nonlinear phase response. That's how nature works. It has nonlinear phase response. You can minimize the system, the linearity error on phase by using the Bessel's approximation of the Bessel model for the analog functions, but analog filters, but it's not nearly as good as say simplest digital filters, since on digital filters you can have exactly linear phase response, and where the linear phase response is required, it's somewhere in here, but anyways, I think it was there. What is maybe I will. Okay, some explanations of the linear or nonlinear phase response. Linear phase response means that I need the draw some formulas again. So I'll continue from that. So you have sine of, well, that should be smaller omega t plus, and of course you have the some amplitude here, and then you have the phase response omega. This is now on a continuous time, but anyways, it's still the same. Mathematics just changes the markings, nothing else. Okay, and if you, well, yeah, if the phase response is linear, meaning a constant k times omega, straight line, it means that combining these, you have a times sine of omega times, well, omegas are the common multipliers, k plus t, meaning that this is also a constant time delay. Okay, so a system, and you have signal, input signal actually having two components. It has a lower frequency component and a higher frequency component. System does, for example, filtering or anything like that. And okay, after the system, you want the time delay of each frequency to be the same in some certain circumstances. For example, if you are carrying the multiple frequency signal, you don't want these different parts of the signal get out of phase. You want to keep them actually happening at the same time. And that can be done only if you have a linear or nearly linear phase response. Extremely important on data transmission with the multiple frequencies. For example, the oldest multiple frequency was the dual tone multiple frequency, the DTMF signal on telephones, and the first modems had the limitations because of the filters actually and the transmission lines. Transmission lines have wavelength dispersion, which means non-linear phase shift. So that was the limiting factor on the original modem lines. Different parts of the signal actually traveled different time. You could not anymore reconstruct the whole package. But of course now there have been some, say, some evolution, or I would say revolution on the data transmission technology, and mostly because of the signals actually are treated, say, digital transmission. And then you can start also compensating for errors, some external errors. Anyhow, so for systems which require linear phase response, you would go always digital. And with the digital, you would go always with the linear phase response systems. Zero phase response, post-processing only, because this actually is a non-causal system. Okay, more ideas around the signal processing. One is the group delay. So practically, if we have a system with the frequency response measured, then the first derivative of this phase response is the group delay. All right, so group delay actually shows the, well, it's actually the delta time. It's the mathematics actually comes up. Then basically you are talking about what is the delay of a signal at different frequencies when they come out on the system. So so if we have a frequency response, h of e j omega, like that. Then we have the phase response, usually negative phase, because we have the that's a passband. Negative phase because of the its delay, and then the group delay. Group delay would look like, well, that part linear, so it's constant, then it goes higher, maybe it goes like that, then it goes lower. So it usually goes something like that for low pass filter. So group delay actually goes lower for higher frequencies, meaning that high frequency components go faster, but the low frequency components near this on the filter edge have the highest variability on the on this transmission time. Okay, so yeah, and nonlinear phase response systems will skew the signal. So if you have the signal pulse shape is a critical thing what you want to preserve, then again the finite impulse response will do it. Infinite impulse response system always actually skew the signal as it shows up in this picture. So if we have a square-shaped input signal to any signal, any system, if the system has linear phase response, then you have a symmetrical. Let me annotate that one. So you have actually this edge and that edge are symmetrical. So when the signal goes up, oops, up here, then it has a certain rise time, it has overshoot here, and before the overshoot, it actually has the undershoot on the beginning, but then it also repeats symmetrically on the falling edge. Okay, nonlinear phase response system. We have rapid rise time. As you can see, this has more delay. It has about, well, the signal delay is about half of the filter width. Here we have less signal delay, but we have overshoot here. Nothing, of course, in here, otherwise it wouldn't be causal. And then basically we don't have the undershoot on the beginning, but we have again it here. So this is not any more symmetric. Oh, actually it's different symmetry here. But anyways, it skews the signal. The signal shape is not symmetrical anymore. This is beautifully symmetrical signal of the box, but then, and this one is kind of hat. Both edges of the hat are the same, but this looks like a French hat. Weird. Sorry. Couldn't help it myself. But anyways, the same signal on zero phase response system. Zero phase response system means that actually I first run the signal through this system, and then I do time reverse of this signal. So this becomes the first signal, and that's the last signal. I filter the same data with the same system. Now this data with the same system. So after that, you actually, if there was a delay here, you will move it back on time, and then you have nice the symmetrical shape, which means that you have again a beautiful hat here. Zero phase response system. So if the you're required to have linear phase response on post-processed signals, then you might actually consider doing it with the IIR systems. IIR systems have non-linear phase response. The only way to get the linear phase response is to have symmetrical finite impulse response system. Okay. Okay, then I think this is the last part. Did we already last time have something about the spectrum analysis? I don't remember, but anyways, if you did, then it doesn't hurt to have it again. So how to analyze a signal spectrum? That's done by Fourier transforming the signal. That's the definition of power spectrum. And in digital systems, we just apply the fast Fourier transformation to calculate the discrete Fourier transformation. And then there's a line of code showing how to calculate the power spectrum of a single input X. But it gets more the content when we go to the exercises. Okay, spectrum analysis example. On perfect analog world, meaning mathematics, this should actually show up as a straight line. Right, it's a single frequency, there's no power in anywhere else. So why on earth we didn't have a single, oops, do I have a draw here? Okay, so why I don't have just a power peak here and nothing else? The reason is actually, well, that will be the sine part of the signal, but we do have actually in real life, we also have the window. So basically we have the multiplication of signals here. The window is simply a box that defines our region of interest. So they look like that box. And inside of that one, there's the sinusoid. Remember from last time, or was it the first time, we have the convolution theorem. If you calculate the convolution in time, it actually, not convolution in frequency, It actually means convolution. What I'm talking about here. So multiplication of signals actually is the same as convolution of spectra. So that real spectrum, what we can see, is practically convolution of this one with, okay, now let's see if I can draw. No. So the spectrum of that box would look like this. And also the left-hand side. Remember, this is symmetric. But this is going to be really ugly. Oh no. Okay, so this is the spectrum of the window box. This is the spectrum of this sinusoid. So actually, this one ends up being this convoluted spectrum in here. So these side lobes here are actually artifacts. Not they're really artifacts. They're features caused by the window. You cannot eliminate those totally, but there are some tricks you can do, but it gives more sense when we go through the go through the filters, and that the filters would be the next time. There. So, but anyways, calculating a signal spectrum always have artifacts, but okay, because of the window what you're looking at the signal, it has a window effects, edge effects, Gibbs phenomenon, if you remember that one from math classes, engineering math. So basically this is the what the spectrum, a single spectrum of sinusoid would look like. Signals which don't change are dull and boring. But there's also something else called spectrogram. So spectrogram is a time series of spectra of subsampled data, px. So here we have a chirp signal. Frequency is changing from 0 to some higher frequency. So I would guess at the end in this picture, it would be the sampling rate. Okay, 0.25. So let's use the annotation tool again. Okay, so if we calculate, okay, let's see, that way somewhere here, the whole, calculate the spectrum at that point, times 0.3, okay, not that one. Let's calculate this spectrum, for example, on, let's see, what is the good color? White would be good at that point. What is spectrum? Well, we take a window around 0.25 on both sides. So we would take a window which looks like something like this. Sorry. 0 is here. Say somewhere in here. Up to 1. Same way here. Okay, that's the sampling window to calculate the spectrum, which I just removed with that white line. So take a subsample, calculate the spectrum, and basically the spectrogram is when you start moving this one by time. So basically, let's start from here. When you start moving this window by time and calculate on each time step, you will actually calculate the individual spectrum and make this a kind of 3D picture. So each of these columns are formed by calculating one spectrum. And actually this one shows, the spectrogram shows how the signal frequency changes by time. Okay, this one was chirp, which means that, okay, it's the kind of sound. And it's quite easily visible for, say, you can imagine what kind of sound that could be. Okay, how about applications of this spectrogram analysis? Now you can actually start matching, for example, vocals, consonants, that kind of stuff, or you can start matching bird sounds and with the library of the measured spectrograms and start the voice recognition. So the voice recognition, hard time to do only in time space, since these are the signals are sinusoid, and you know what happens if you, for example, try to calculate the signal product of two sinusoids and integrating it. Most of those products will be zero, so it's hard to make the correlation analysis of that kind of signals, but it's relatively easy to do the spectrum analysis of that kind of, since the after all, voice is not carrying time-based information, but it's a spectrum information. Well, it varies by time, but of course, but anyways, it's a the information has at least two dimensions. I think it was 2.31 dimensions or something like that. But anyways, that's a philosophical question. So, okay, the spectrogram is a tool to start doing the voice recognition. Okay, for this session, I also have these questions for self-study. But anyways, we have been now working more than 1 hour now. So let's have a break. And let's see, we could try to continue at 12 o'clock your time, unless you have any questions. Anyways, I will stop recording.